Between 1960 and 1993, the chemist Alexander Shulgin synthesized and personally tested nearly 200 novel psychoactive compounds. He cataloged his findings in highly detailed analog laboratory notebooks. These archives contain decades of unstructured, first-person narrative data. The primary measurement tool in these records is the Shulgin rating scale, a qualitative system ranging from +1 to +4. This reliance on first-person narrative creates a computational impasse. Modern scientific modeling cannot parse a subjective description of a psychological state. It requires standardized, machine-readable inputs. Because the archive is framed through subjective experience, a massive volume of historical scientific data remains unusable for contemporary neuroscience without retroactive translation. Modern neuroscience operates on third-person objective metrics. This diagram illustrates the data gap. A subjective report of a shimmering visual field doesn't translate to the receptor matrices required by current research. The immediate necessity is filling these blank cells with valid biological values. The overarching objective is exact completion, the deployment of a custom software-hardware stack to map 20th century phenomenology to 21st century neurobiology. Layer 1 of the stack is a software extraction engine built on the open-source Neo-Vertex-1 architecture. This layer performs text-to-SAR, or structure-activity relationship conversion. Using a retrieval-augmented generation pipeline, the software scans historical archives to output predicted molecular binding profiles. This extraction process can reconcile long-standing historical contradictions, such as the 1967 paradox involving the compound DOM, or STP. Early Dow chemical toxicology reports cited the duration of DOM as 24 hours, yet Shulgin's subjective bioassays recorded the effects ending between 14 and 20 hours. The AI software resolves this by modeling molecular metabolic half-life against the subjective receptor desensitization described in Shulgin's notes. Given the density of Shulgin's narrative archives, algorithmic extraction is the most efficient method for translating analog records into standardized pharmacological structures. Software predictions are validated using real-time biological hardware. Layer 2, the Science BCI ecosystem. Axon probes capture high-density spike recordings directly from active cortical layers. This resolution is required to track biased agonism, which explains why two compounds with identical receptor affinity can produce vastly different subjective experiences based on which proteins they recruit. This table compares the biased ratios of specific phenylethylamines. High-fidelity hardware allows us to record the neural signatures of this chemical divergence. Using these BCIs, researchers can objectively record the distinct neural signatures generated by specific molecular biases. Layer 3 is the cognitive visualization framework, responsible for decoding the raw neural signals captured by the hardware. The system utilizes a human-in-the-loop feedback loop, allowing subjects to interact with their own real-time neural data. Through a process called directed visualization, the system translates internal, geometrically complex subjective states into communicable external visual data. This layer translates invisible neurobiological electrical activity into the specific visual phenomena cataloged in the Shulgin archives. The foundational layer 4 consists of safety and integrity gating driven by neurobiological controls. Using orexin sleep baseline models, the system establishes a subject's default state of consciousness. This diagram compares standardized REM sleep frequency waves against drug-induced neural oscillations. Deep learning analysis identifies neural deviations that indicate true pharmacological effects rather than baseline sleep intrusion. This rigorous gating ensures the stack imputes historical data based on isolated chemical variables rather than physiological noise. AI extraction, BCI recording, cognitive visualization, and biological gating now operate as a single unified pipeline. The primary function of this stack is not simply archival storage, but data imputation. Returning to the logic model, we can see how the pipeline connects these disparate datasets, successfully filling the pharmacological lacunae left by 20th century analog methodologies. This synchronized pipeline achieves the exact computational completion of the Shulgin corpus. Subjective analog records are now mathematically bound to objective molecular communication metrics. The final output of this process is a standardized, fully queryable, three-dimensional map of the entire human receptorome. By architecting the completion of these archives, This system provides the computational foundation required for high-precision neuropharmacology and AI engineering.